Hello guys, today in this video we are going to discuss about minority carrier distribution in forward active mode of a bipolar junction transistor, particularly an NPN bipolar junction transistor. Okay, so let us draw the basic diagram of a bipolar junction transistor that we are going to use. So basically we have the emitter region, which is N region, and then the neutral base width of this region, let us take it as XC, one-dimensional width we are considering. So let us give a scale to this, taking X dash as the variable as the scale, XE, and this is X dash is equal to 0. So this XE represents the neutral base width in the emitter region. Then we have the NP junction. The base region is a P region, and this is the junction, emitter base junction. And then we have XB, which is neutral base width region. So neutral base width region, let us give a scale for this. X is equal to 0 to X is equal to XB. Then we have another collector region. So collector region is C, okay, with the N region, and the neutral collector width, we will take it as XC, and I will put the scale as here from this, which is X double dash, we will take 0 to this is X double dash is equal to X is C. So C is the neutral width of the collector. Okay, so this is how the basic diagram looks like in terms of the neutral emitter width, neutral base width, and neutral collector width. So these XE, XB, and XC are the neutral emitter, base, and collector. Okay, so neutral widths in this region. Okay, so the other thing that we need to discuss is the distribution of minority carriers in a forward active mode in all these regions. So let us consider the emitter region first. Okay, this is our emitter region. Okay, then the junction between the base and emitter. Okay, then the base region. Okay, and then the junction between the base and collector. Okay, and then the collector region. Okay, so now exactly the same way we will write whatever we have, whatever scales we have taken. X dash is equal to XE, and here we have taken X dash is equal to 0. That's the neutral emitter region. X is equal to 0 to X is equal to XB. That's our base region. And X double dash is equal to 0 to X double dash is equal to XC, the collector bit. Now, let us now see how the magnetic carrier concentrations will look like. This is emitter region, which is a N region. This is the base region, which is the P region. This is again the collector region, which is N region. Now, in the forward active mode, base emitter junction is forward biased. So the concentration of magnetic carrier here, that is the holes, will be maximum, and it will vary from maximum hole concentration to the thermal equilibrium concentration of holes in the emitter region. Thermal equilibrium concentration of holes in the emitter region, let us consider this to be PE0. For more detail, for more explanation, you need to understand how the magnetic carriers are distributed in the PN junction diode in all the, like forward bias condition, reverse bias condition. You need to go and revisit the video that I have uploaded for PN junction. Okay, magnetic carrier distribution NPN junction. That will give you more idea about this, why I'm showing the concentration this way. So PE0 is the thermal equilibrium hole concentration in the emitter region. Here it is maximum. It will vary from this value, maximum value, to this. Okay, reduce down, drop down to PE0. Okay, let us define this function, which is PE, the whole concentration in the emitter region. Okay, a function of x dash, that gives us how the magnetic charge carrier is actually varying in this region, emitter region. Okay, and mathematically, if you have visited that video, we got the value. We can write the value as PE x dash at x dash is equal to 0, right? The maximum value here, okay, that can be written as PE0, which is the thermal equilibrium concentration, e to the power, okay, exponential of E VBE, the base emitter voltage, divided by KT. Okay, that's the concentration here, and it will drop down to PE0, okay, in the emitter region. Exactly same way in the base region, here as it is forward bias, the concentration will be NB, so magnetic error concentration will be locked on here at x is equal to 0, can be written as NB0, that is the thermal equilibrium concentration of magnetic carriers in the base region, which is NB0, and then exponential of e to the power, the same way the base emitter voltage EBBE upon KT. Okay, this is that. Then the base and collector region. Base collector junction is reverse biased. So reverse bias, so from here, from the maximum concentration, it will come back to the original, thermal equilibrium concentration NB0, and then further to 0, because it is reverse biased. So the magnetic carrier concentration at the edge of the junction will be 0 here. So it will vary. You need to refer to that reverse biased. This is not a straight line, but it's a exponential graph. Let me redraw it. So you can see graph like this. Okay, this is the function. We can define this function as NBX. These are all exponential functions. You can see that. Okay, so draw the exponential curve. And then we have in the collector region, this is also reverse biased, and the concentration, thermal equilibrium, magnetic carrier concentration of holes in this region, let us take as PC0. P is for holes, C for collector region, O for thermal equilibrium, or PC0, you can consider that. Okay, so here it will be 0 because that's the edge of the reverse biased junction, and here it is the maximum value. So draw the graph like this. Draw the graph like this, which is a function defined as PCX double dash. It varies with X double dash, right? So this is the basic, magnetic carrier distribution. Okay, a schematic diagram that will give you the idea how the functions varies, and using this we will be able to find out the excess carrier concentration of these, holes or the electrons, right, in different regions, right? So what are the notations we used here is, you can see PE0, NB0, PC0. These are the thermal equilibrium magnetic carrier concentration in emitter, base, and collector. Okay, and then this PX dash, NBX, and PCX double dash, these are all steady state magnetic carrier concentration in emitter, base, and collector region. Let me write this for you. PE0, we said PE0, NB0, PE0, NB0, and PC0. These are thermal equilibrium minority carrier concentrations in emitter, base, and collector regions. Okay, and then the functions we said the steady state, that is, we define Px double dash, which is your P0 exponential of EV by KT, right? Similarly, we defined NBx, we defined PCx double dash. These are all steady state minority carrier concentrations in emitter, base, and collector results. Okay, so these are the functions we defined. Now, let us discuss about the base region first, right? So this is the base region. The concentration varies from NB0 exponentially BV by KT to 0, okay, at x is equal to 0 to x is equal to xb, right? So we have the NBx, right, as the function. We have the thermal equilibrium concentration, which is NB0, and we can find out what is the excess minority carrier electron concentration in the base region, which is actually a p region. So electron will be considered as the minority carrier there. Okay, so we will, if you have revisited the minority carrier distribution in p-n junction, I'm going to use the same equation that we have derived there. Okay, so for the base region, we have derived the steady state excess minority carrier electron concentration. Okay, so that we can write for the base region. I'm writing, so the diffusion coefficient dB in the base, for the base region, del square delta NB x, delta NB I have taken as the excess minority carrier electron concentration, del x square. Okay, and then delta NB when tau b0, this is equal to 0. Okay, so what I used, what are the functions? I mean, delta NB, this is our excess minority carrier electron concentration. Why we said excess magnetic carrier electron concentration? Because the junction is biased. You can see the base emitter junction is forward biased. As a result, the electron concentration in the base region has increased from NB0 to NBx. So the excess magnetic carrier concentration can be determined by taking the difference between NBx at any point in this base region. What is the value of what is the value of electron concentration? Right, minus NB0, the thermal equilibrium concentration, that will give us the excess magnetic carrier electron concentration, right? Then dB is the minority carrier diffusion coefficient, that we have already discussed in what is diffusion coefficient, right? Okay, in PN junction, you can revisit what is that diffusion coefficient to understand it in detail. Then tau B0 is the lifetime of this minority carrier electron concentration in the base region. Okay, lifetime in the base region, or how long they will exist, okay, before disintegrating from NBx to 0, right, at x is equal to 0 to x is equal to xb, okay, the scale that we have taken, the neutral weight. Okay, let us now do the maths. Delta NB for any x is given as NBx, the non-equilibrium concentration of the magnetic carrier, minus the equilibrium value NB0, right? Then we have this, if I will take delta NB is only the variable of X without considering the doping profile and all, a recombination of the magnetic carrier concentration. We are considering only the excess carrier as a function of X. So here in this equation where we have taken the partial differentiation with respect to X, considering that delta NB may vary or may depend on any other variable, if you are not considering that and only considering delta NB is a function of X only, then this partial differentiation can be written as ordinary differential equation. Okay, so considering delta NB as a function of X only. Okay, so I will rewrite the equation. Okay, then we have this dB, the diffusion coefficient, del square of rewriting and delta NB, rewriting the equation upon del x square minus delta NB x upon tau b0 is equal to 0. This was our equation. Now I'm writing this equation with dividing by dB and converting the del square upon del x square to d square upon dx square, considering delta NB as a function of x only. So we can write d square of delta NBx, okay, upon dx square minus delta NBx dB tau b0 divided with dB. This is equal to 0. Right? Then we have, I'm rewriting this, d square delta NBx dx square. The only change I'm going to write over here, NBx, mark this, dB and tau b0, this terminology, dB and tau b0, we are writing it as LB square is equal to 0. What is this LB square? LB square we wrote for we wrote it for dB tau b0, dB tau b0, okay, where this LB can be square root dB tau b0. And what is this LB? LB is the carrier diffusion length, okay, in the base region. Okay, so what does it mean? Basically, dB gives us the diffusion coefficient, right? So how well the magnetic carrier can enter inside this region, base region. So that is given by dB, and tau b0, it gives us till what time it will exist, right? So it's, if I will multiply dB and tau b0, this factor is associated with the diffusion length, till what distance the magnetic carrier can enter in the opposite region, right? For example, the excess magnetic carrier is electron here. So how this electron concentration will, will enter or will exist, okay, in the base region. That will give, that can be determined by finding diffusion coefficient multiplied with tau b0, which is the lifetime of these magnetic carriers in the base region. Multiplication of this will give us the LB square. Taking the square root of this will give us the carrier diffusion length in the base region. Okay, so this is a general, you can see a ordinary differential equation, this whole thing. This is ordinary differential equation. You can see this, right? We can write a general solution to this differential equation. Okay, it's in the form of, you can say, d square y upon dx square minus, right? um, some constant minus some constant times y is equal to 0. Okay, so if you will see, this is very simple second order ordinary differential equation whose general solution can be written. Okay, so we can write the general solution to this differential equation above, that is boxed. Okay, can be written as, so delta NB is our variable, delta NB as a function of X can be written as a e to the power, okay, which I'm writing this way, x upon lb plus b exponential of minus x upon lb. Okay, this is a general solution. If you take this y to be this, then you find d square y upon dx square minus some constant which is 1 by lb square times y is equal to 0. So the general solution, we have taken this, and you find d square upon dx square of this, and then you minus 1 by lb square of delta n bx, you will get 0. That's why we said the general solution of this differential equation, considering a, b, some random constants, right? This will satisfy the differential equation. Okay, that's why we consider this to be the general solution. Okay, so once you get the value of delta n b from the general solution, putting the boundary conditions, we will be able to determine the value of a and b, and then we can substitute it, okay, to know the exact value of delta and b. We have the exponential of x by lb, exponential of minus x by lb. A and b are the random constant that we have chosen. We do not know the value of a and b, but mathematically we can substitute some conditions, initial conditions, and then we will be able to determine a and b from this and then substitute. This is the normal way of solving a differential equation. So let us use the boundary condition. The first thing that we know in the base region is delta NB. What is the magnetic carrier concentration? Delta NB at x is equal to x0. We will substitute in the general solution, and delta NB at x is equal to xb. So we will substitute the value of x as xb in the general solution and rewrite. Okay. So from this, if I'll substitute delta NB at x is equal to 0, then we got, okay, this as a exponential. You substitute x as 0 here and x as 0 here, so e to the power 0 here, also e to the power 0 minus 0, which is 0. That will give us a plus b. Okay, the second one, we said x is equal to xb. Will substitute delta nb at x is equal to xb. If I'll substitute, we will rewrite a e to the power, in place of x we will substitute xb upon lb plus b e to the power, we will substitute minus xb, x as xb upon lb. Okay, so this is what we got. Fine. Now what is the value of delta nb at x is equal to 0? So that also we know, delta nb, we have written the actual value of delta nb, which is your non-equilibrium concentration minus the thermal equilibrium concentration, that is nb at x, and minus thermal equilibrium concentration, which is nb0. Okay, let us write that way as well. So delta nb at x is equal to 0 can be written as nb, non-equilibrium value at x is equal to 0, minus nb0. So that nb at x is equal to 0, if you remember, we have written here as nb0 exponentially v by kt, this one. Substitute this value. So substituting that value here, we can write nb0 exponential of e bbe upon kt minus nb0, take nb0 common, nb0 out, you got exponential of evbe upon kt, okay, minus 1. Okay, this we got. Similarly, in the second boundary condition, delta nb is at x is equal to xb, was nb at xb, or x is equal to xb minus nb0, the same way. So that was 0 because reverse bias condition of a base and collector region. So it was varying from a maximum to maximum, this value to 0. So we can substitute that 0 here. So nb at x is equal to 0 and minus nb0, that gives us minus nb0. Okay, so equate these things now. So a plus b is equal to this at x is equal to 0, and at x is equal to xb, this is equal to minus nb0. Equate these two. So a plus b is equal to nb0 exponential of E VBE divided by KT minus 1. That's our equation 1. And similarly, the other, if you liquid A exponential of XB upon LB plus B exponential of minus XB upon LB is equal to minus NB0. Okay, that's another equation. Okay, then we need to just solve these two. A plus B is this. So if you can multiply exponential of xb by lb in equation 1, right? And then if you subtract these two, so let us take equation 1, whatever equation 1 we have written, multiply it with xb upon lb and write the value. So I got a exponential of xb by lb plus b exponential of xb by lb is equal to nb0 exponential of evbe by kt minus 1. Okay, multiply it with exponential of xb by lb. This is what we got, right? Write it as equation 3. Okay, and then subtract equation 2 from 3, okay, to determine the value of the constants. That was our objective. So if you'll do that, b exponential of xb upon lb, right, minus exponential of minus xb upon lb, okay, this is equal to nb0 exponential of EVBE upon KT minus 1, right? And then we have this exponential multiplied with XB upon LB, right? Plus NB0. Okay, this is what we got, 3 minus 2. And now we can determine, making B the subject, we can write what is B. So B is equal to NB0 e to the power, here we got EBBE upon KT in bracket minus 1 bracket n exponential of XB upon LB plus NB0 whole divided by this thing. This is nothing but 2 sine hyperbolic XB upon LB. Okay, so we got the value of, exactly the same way we can determine the value of B by just multiplying exponential of minus XB by LB to equation 1, and then again do the same process of subtracting and making A the subject, and do the same thing. I'm not doing it, you can determine it. I'm just writing the value directly. Minus NB0 is found to be, this is minus NB0 e to the power EB B base emitter voltage upon KT minus 1 multiplied with exponential of minus XB upon LB. Okay, so this whole divided by exactly the same thing, 2 sine hyperbolic XB upon LB. Okay, now you have the values that we have taken as random earlier. Now we could determine the values of A and B by putting the boundary conditions. Now substitute these values in delta NB in the general solution of the delta NB that we had written. So delta NB is your whatever determined value of A, right? I will rewrite this 1 second. Okay, so we have delta NB as minus NB0, substituting the A value again, rewriting it, minus NB0 exponential of EVBE upon KT minus 1 e to the power minus xb upon lb, right? Whole divided by 2 sine hyperbolic xb by lb that we determined for our a, multiplied with the general solution was a exponential of x by lb. So this is the first, okay, term, and the second term we need to substitute the value of b, which was nb0 exponential of evb upon kt minus 1 multiplied with e to the power xb by lb, right, whole divided by 2 sine hyperbolic xb by lb. This was our value of b multiplied with, again, exponential of minus x by lb. This is your delta nb as function of x. Okay, so you got the magnetic area concentration here. Okay, then further you can reduce it, okay, by taking nb0 common and further simplifying it. We can write this as nb0. You have to be little patient while doing this. Okay, it's very simple, but so many variables we are putting in brackets. Minus 1. Okay, take this out, and then we have e to the power xb minus x divided by lb minus exponential e to the power, taking minus out, xb minus x divided by lb minus x by lb minus exponential of e to the power minus x by lb, right? Okay, bracket end. This big whole divided by have 2 sine hyperbolic xb by lb. This is what we got in the bracketed terms. You got e to the power xb minus x by lb here, minus x e to the power minus xb minus xb. So that will give us one hyperbolic term. This one will give us some hyperbolic term. So it can be reduced to nb0 in the bracket. We got the first term will be there as it is, ebbe upon kt minus 1 multiplied with 2 sine hyperbolic xb minus x upon lb minus 2 sine hyperbolic x by lb. Okay, that's where it ends. All divided by 2 sine hyperbolic xb by lb, which will give us nb0. Finally, we got to the power evbe upon kt minus 1 sine hyperbolic, okay, cancelling 2 from numerator denominator, xb minus x upon lb minus sine hyperbolic x by lb, okay, bracket end. And then your sine hyperbolic xb upon lb. Okay, this is what we got, right? This is our final expression, but we can do a little more modification. Okay, this is the expression for your delta nbx. Okay, this is the expression for delta nbx, that is for the excess magnetic carrier electron concentration in the base region. But with an approximation, for example, if you consider the neutral base width, which is xb, okay, is very less than lb, that is the diffusion length till what distance it can penetrate in the base region, And of course x any point, because you have x is equal, the base width varies from x is equal to 0 to x is equal to xb. So definitely if xb is less than lb, then x will also be because x lies between 0 and xb, x will also be less than lb. Okay, so if this assumption we will take, then using this approximation we can write sine hyperbolic x is nearly equal to x for x very less than 1, right? So whenever we have a ratio of that, x by lb or xb minus x by lb, we can consider it to be very less than 1. Okay, so as we know this sine hyperbolic x. Why we did this? Sine hyperbolic x, if we'll expand, it is actually x plus x cubed by factorial 3 plus x to the power 5 upon 5 factorial, like this. So for very small value of x, okay, x less than 1, we can ignore these higher orders and we can just write sine hyperbolic x is equal to x, right? So now substitute this here, this approximation, considering x to be very small, then xb and x both are very small than lb, the diffusion length. Okay, this will be nearly equal to what? nb0. Here I'm substituting wherever we have sine hyperbolic x, I'm writing it as x only, right? nb0, we have in the bracket exponential of evbe upon kt minus 1 bracket close, and this one I'm writing it as xp minus x, the hyperbolic term I'm writing as x only, lb minus x by lb. This is to simplify it further, whole divided by, this is xb by lb. Wherever sine hyperbolic was there, we are writing it as x. Okay, now so this is nearly equal nb0 upon lb. Okay, we have this exponential of EVBE upon KT minus 1 XB minus X minus X. Okay, what we did here, all divided by XB upon LB. Okay, so we took the LB in the terms here to outside, and then we derive. So delta NBX is approximately NB0 divided by XB, cancelling our LB. Now you can see this as exponential EVBE upon KT minus 1 XB minus X minus x. Okay, so you can see how we simplified this under a condition where we considered xb is less than lb, right? So this is our minority carrier concentration in the base region of an NPN bipolar junction transistor. Okay, for the base region we did. We will exceed the time. If you will consider for the collector and emitter region in this video, it will be very lengthy, so I'm just keeping it here. Okay, that we derived the magnetic area concentration for the base region in this particular video. We'll continue with the other regions for collector and emitter regions in the next video. Thank you.